Hello my dear students. Hi everyone. Having discussed the classification and the general methods of preparation of alcohols, now in this lecture we are going to discuss the physical as well as the chemical properties of a class of compounds known as alcohols. So first we'll take up these properties of alcohol. Before starting with these properties of alcohol, let me have some structural idea about these alcohols. So we are focused on alcohols. We have look at this R O H. This is alkyl group, oxygen, hydrogen. The oxygen is having two lone pairs of electron. So the carbon of alkyl group, we have this alkyl group. In this we have carbon. So this carbon is sp3 hybridized. So this carbon, which is directly bonded to OH, being sp3 hybridized, this has to be tetrahedral. And similarly, look at this, the central atom oxygen is again undergoing sp3 hybridized. So both the carbon of alkyl group and the oxygen is sp3 hybridized. Now the carbon of alkyl being sp3 hybridized, this is tetrahedral structure. But when we look at the structure of this oxygen, though we have sp3, the shape of the geometry of the molecule will be sp3, that is tetrahedral, but the shape will be something different. So this ROH bond is bent molecule like water. So we have this, we have lone pair here. This is lone pair electrons. Now look at this. These sp3 hybridized oxygen, we have 4 hybrid orbitals. Out of these 4 hybrid orbitals, 2 hybrid orbitals are involved in formation of bond, that is carbon oxygen bond and oxygen hydrogen bond. So this bond is formed by sp3 of carbon and sp3 of oxygen. This bond is formed by sp3 of oxygen and S of hydrogen. So look at this. This is by sp3 of oxygen and S orbital of hydrogen overlap, giving you sigma bond. This carbon oxygen bond, this is all formed by sp3 of carbon overlapping with sp3 of oxygen. After involving these two sp3 hybrid orbitals in formation of bond with carbon of alkyl group and hydrogen, oxygen is left with 2 hybrid orbitals, and each hybrid orbital occupies a pair of electrons, which is known as lone pair of electrons. So these are lone pair electrons, and look at this, these 2 lone pair electrons undergoes lone pair repulsion. So we have a lone pair repulsion. Because of this lone pair repulsion, the bond angle, which was supposed to be 109.5, that is perfect tetrahedral angle, this bond ROH bond, this bond is less than 109 degree due to this lone bond pair repulsion, and in fact this bond angle is approximately 108.9. So this is less than tetrahedral angle, and we say this is due to lone pair repulsion. So this is the general structure of alcohols. So alcohols are not linear molecule, but a bent molecule. that is angular shape. Bond angle is both carbon and oxygen is sp3 hybridized. Carbon oxygen bond is sp3 overlap. Oxygen hydrogen bond is sp3s overlap. The bond angle is less than tetrahedral angle because of this lone pair repulsion. So this is the general structure of alcohols. Now coming to the properties or the physical properties. Physical properties of this class of compounds known as alcohols. Now, in physical properties, we'll take up the boiling point. So first take up that is boiling point. Now, the boiling point of these compounds called alcohols are generally high when we compare with other compounds like haloalkanes or hydrocarbons with similar molecular mass. So I am again repeating them. The boiling point of alcohols is generally higher than those of haloalkanes or hydrocarbons having similar molecular mass. The reason being, these alcohols are associated through intermolecular hydrogen bond. So because of this intermolecular hydrogen bond, the boiling points of alcohols are generally high. As the boiling intermolecular hydrogen bond strength increases, the boiling point also increases to generally high than those of haloalkanes or hydrocarbons than those of haloalkanes or hydrocarbons with similar molar mass. And the reason for this is due to association through intermolecular hydrogen bond. So look at this, we have this. So this oxygen is hydrogen bonded to this hydrogen of another molecule, and this keeps on extending. So because of this type of intermolecular hydrogen bond, the boiling point of alcohols are generally high. But if you look at this, when we compare the boiling points of isomers, we will compare the boiling points of homologous series. Now, for homologous series, as the molecular mass increases, the surface area also increases. The intermolecular attractive force along with this hydrogen bond also increases. As this molecular mass increases when we moving on a homologous series, the boiling point also increases. For homologous series, so homologous series means series of compounds with same molecular or the similar molecular formula. For homologous series, boiling point increases with increase in number of carbon atoms or increase in molar mass. As I told you, for with increase in carbon atoms, the surface area increases. As the surface area increases, intermolecular attractive force increases, boiling point also increases. The reason is surface area increases. As the surface area increases, intermolecular attractive force increases. boiling point increases. This is for homologous series. Now coming to isomers, same trend we have given in alkyl halides also. For isomeric alcohols, the boiling point increases as the surface area increases, or we say with increase in branching, the surface area decreases, boiling point also decreases. For isomeric alcohols, boiling point decreases as the branching increases. So the reason is, with increase in branching, surface area decreases. So with decrease in surface area, the intermolecular attractive force decreases. So look at this example. Take this CH3, CH2, 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 that is N-butyl alcohol. Then we have ice. So look at this, we have branching here, and take this so with increase in branching, the molecular surface area decreases. As the surface area decreases, the intermolecular attractive force decreases. As the intermolecular attractive force decreases, the boiling point decreases. So when we compare this isomeric alcohols with increase in branching, boiling point decreases. So this is the variation in boiling point. So again I am telling you, the boiling point of these compounds are generally high due to this association through hydrogen bond. Which type of hydrogen bond? Intermolecular hydrogen bond. But when we compare for isomeric, then we have to see the branching in the chain. With increase in branching, molecule assumes spherical in shape, that is surface area decreases, intermolecular attractive force decreases, boiling point also decreases. But for homologous series, is the mass of the substance increases, or as the number of carbon increases, boiling point increases because of increase in surface area, intermolecular attractive force increases. So this is how the boiling point of these compounds called alcohol varies. Now coming to solubility of these compounds, solubility of these compounds, lower members, again one more point here, if we have the number of OH groups increases, then the association through hydrogen bond also increases, the boiling point will also increases. So solubility, the lower members of this class of compounds are very much soluble in water. Again we say this solubility is due to the intermolecular hydrogen bond formed between alcohol and water. But as the size of alkyl group increases, or as the molecular mass increases, the alkyl part, that is hydrophobic part, increases, solubility decreases. So, lower members are highly soluble. So this is due to soluble in water, So this is due to intermolecular hydrogen bond with alcohol and water. So we have this. This is alcohol. This is water. So we have this association through hydrogen bond. But as the size of alkyl group increases, solubility decreases. With increase in the size of alkyl groups, solubility decreases. So this is a general trend. With increase in the size of carbon alkyl group, hydrocarbonic part, it is hydrophobic part increases, so solubility decreases. Alcohols with more number of OH groups are more soluble. So when we compare this, more the number of OH groups, more is the solubility, that is more number of intermolecular hydrogen bond. So when we compare, look at this, that is ethanol, that is ethanol. Then we have, look at this, glycol, ethylene glycol. So we have one OH group, we have two OH group. Then we have, look at this, glycerol. Number of OH groups increases. This is monohydric, dihydric, trihydric. So as the number of OH group increases, association through intermolecular hydrogen bond increases, solubility also increases. Then for isomeric compounds with increase in branching, solubility also increases. For isomeric compounds, solubility increases with branching. Again, with increase in branching, surface area decreases, and this can be easily surrounded by more number of water molecules, hence the solubility increases. So look at this. This is tertiary butyl alcohol. And when we compare the solubility of tertiary butyl and this is iso. So we have this isomeric. So we have this branching, isopropyl, tertiary butyl. So with increase in branching, solubility increases. So this is how the solubility of this class of compounds known as alcohols varies. So again, solubility of with water is due to association through intermolecular hydrogen bond. So this is about the physical properties of alcohols. Now from this we'll move on to the chemical properties of alcohols. Now coming to the chemical properties of these alcohols. To define these chemical properties, we have to look at the polarization of the bond in alcohols. Now, oxygen-hydrogen bond is again polarized. Hydrogen being less electronegative than oxygen, oxygen equals partial negative, hydrogen equals partial positive. So, this polarization of OH bond gives rise to the acidic nature of alcohols. So this polarization OH bond So in many of the reaction, this OH bond may undergo breaking. So if this OH undergoes breaking, then there is a tendency for release of H plus ion in solution. So this polarization of OH bond gives rise to acidic nature of alcohols. And again, if you look at this RO bond, carbon oxygen bond, is again polarized. Oxygen is more electronegative than carbon. So oxygen again negatively polarized, carbon positively polarized. This polarization of RO bond gives rise to breaking of RO bond. If RO bond breaks, then this bond breaking shows the basic property or the basic nature of alcohols. So then depending on which bond is to be break, if RO bond breaks, this was acidic property. If RO bond breaks, then basic nature of alcohol. If OH bond breaks, then again this shows the acidic property. See, all this depends on the polarization of carbon oxygen and the polarization of oxygen hydrogen bond. So apart from this breaking of OH bond and RO bond, alcohols also say some other reactions like oxidation, reduction, and the reaction at alkyl part. But the most important reaction is breaking of OH bond and breaking of RO bond. So first we'll take up breaking of OH bond, that is the acidic nature of alcohols. Acidic nature of alcohols, that is OH bond breaking. You have to break this OH bond. So before breaking this, let's define the acidic nature of alcohols. So in this alcohol, ROH, pure alkyl group. This alkyl group is electron released by induction. As this releases electron density, this increases electron density in oxygen. When this increases electron density on oxygen, the electron withdrawing character of this oxygen decreases, acidic character decreases. So these are being electron positive, acidic character decreases. So if R contains any electron withdrawing group, then acidic character will increases. So plus R being plus I, acidic character is less. So minus I groups increases the acidic character. So when we look at this, RCH2OH, that is primary, and we have RCHROH, that is secondary, and RCR, that is tertiary. So as the number of alkyl groups on carbon having oxygen increases, electron releasing character increases. As the electron releasing character increases, the acidic character of alcohols decreases. So this is the acidic nature of alcohol. Primary alcohol is the most acidic, tertiary alcohol is the least acidic. When we say this is acidic, after removal of H plus ion, this is converted into conjugate base. So we have conjugate base RCHRO minus RCCO minus. So this is conjugate base. So when we compare the conjugate base, tertiary alcohol being weakest acid is conjugate base is the strongest base. So when we compare the strongest basicity or the basic character of conjugate base, as the number of alkyl groups increases, the basic character also increases. So this is acidic character. If you look at this, CH3OH, CH2Cl, CHCl2, C Now we keep on removing hydrogen. So this is purely alkyl group. So this is electron releasing group. When this hydrogen is replaced by Cl, this becomes minus I group. Now as the number of electron withdrawing group increases, minus I character increases. So CCl3 is a very strong electron withdrawing group. So as the minus I group increases, acidic character also increases. Similarly, look at this. When we compare this CH3, CH2Cl, OH, CH2, F, OH, fluorine being more electronegative than chlorine. So this CH2FOH will be stronger acid compared to that of CH2ClOH. That means the acidic character increases as the number of minus I groups increases on carbon bearing oxygen. So this is the acidic nature of alcohols. When we compare the acidic nature of different compounds, look at this. This water is more acidic than alcohols. Alcohols are more acidic than acetylene, and acetylenes are more acidic than ammonia, and ammonia is more acidic than CH4. Now take this conjugate base OH minus, RO minus, CHC minus, NH2 minus, CH3 minus. So water being the strongest acid, OH minus is the weakest base, CH4 being CH bond, they being the weakest acid, so C minus will be the strongest base. This is the basic character of this anions. So this is how we compare the acidic nature of alcohols. Now after this, we'll take up some reactions in which this alcohol shows acidic nature. So we have to rub this. So one of the most important reaction which shows acidic nature of alcohol, this is a reaction with electropositive metals like sodium, potassium, aluminium, etc. So look at this, we have this alcohol. Alcohols react with this highly electropositive metal like sodium, potassium or aluminium. Well, look at this, this gives you RO minus Na plus. So that means we are breaking this bond, and this gives you hydrogen gas is released. So reaction of alcohols with sodium metal. So 1 mole of alcohol reacts with 1 mole of sodium metal to give you half moles of hydrogen gas. So from this, the number of moles of hydrogen gas released, we can also correlate how many acidic hydrogens are present in the given alcohol. Similarly, we can have a look at this potassium. Take this potassium. We can again RO minus K plus plus half hydrogen. Take this with magnesium. But look at this ROH reacts with magnesium when we get RO minus 2 Mg 2 plus. So the valency of magnesium being electrovalency being 2, so this 1 mole of magnesium must react with 2 moles of alcohol, and this gives rise to 1 mole of hydrogen. Here the electrovalency changes, so 2 moles react means there are 2 mole acidic hydrogen which gives rise to 1 mole of hydrogen. Take this ROH reacts with aluminium. So the electrovalency of aluminium is 3. So RO minus has to be 3. So 3 moles of alcohol must react with 1 mole of this aluminium metal, when this gives rise to 3/2 moles of hydrogen gas. So this is how we correlate with the number of moles of hydrogen formed in the product with the number of acidic hydrogens present in the given alcohol. So this is the reaction with electropositive metals. So this reaction shows the acidic nature of alcohol is very weak. So these cannot react with so-called strong base like sodium hydroxide, potassium hydroxide. See, let's see why this is so. Alcohols, we are saying alcohols are acidic, but these cannot react with sodium hydroxide to give you RO minus Na plus H2O. Why this is? Look at this. We have seen here water is stronger acid than alcohol, and RO minus is stronger base than OH minus. So look at this. We have a strong base, we have a strong acid. So this is weak acid, this is weak base. So weak acid, weak base cannot react to give you strong acid, strong base. So this reaction is not feasible in the forward direction. But this reaction is feasible in the backward direction. So basic character of base, RO minus is stronger base than OH minus. Alcohol is a weak acid than water. So weak acid, weak base cannot react to give you strong acid, strong base. So this is the acidic nature of alcohols, which proves by a reaction with strongly electropositive metals of group 1 and group 2. Take the second reaction here. And this reaction is a name reaction. This is very important name reaction of alcohol, that is Fischer esterification reaction. So generally this reaction is given as, we have this RC double bond OH, that is acid. This reacts with alcohol, this is alcohol. So the reaction of acid with alcohol in presence of mineral acid, normally sulfuric acid is taken as the catalyst. This gives rise to esters, that is esters plus H2O. So this reaction of carboxylic acids with alcohol in presence of sulfuric acid giving rise to esters and water. This reaction is known as Fischer esterification. In this reaction, OH group from carboxylic acid and H plus ion from alcohol is removed. So in this reaction, alcohol shows acidic property and OH is coming from the acid. So this reaction being reversible or an equilibrium reaction, the quantity of ester formed will be very less, because the moment ester is formed, this again reacts with H2O in presence of acidic medium, gives rise to acid and alcohol. So we have an equilibrium or a reversible reaction. Now to increase the yield of this ester, the water formed in the reaction is to be continuously removed. If the quantity of water, if the product water is continuously removed, then the equilibrium will be disturbed. According to Le-Chatelier's principle, if the product is removed continuously from an equilibrium mixture, the reaction equilibrium shifted to the forward direction. If the reaction equilibrium is shifted to forward direction, the quantity of esters is increased. So this is the reason why during Fischer esterification reaction, the water as formed should be continuously removed. That is, to increase the yield of ester or to shift the equilibrium in the forward direction. So keep in this mind. Sorry, keep this thing in mind. Now in this reaction, alcohol is showing acidic behavior. So since alcohol is showing acidic behavior, the reactivity order of alcohol will be methyl alcohol will be the most reactive, followed by primary, followed by secondary, followed by tertiary. So the least reactive alcohol for this Fischer esterification reaction will be tertiary, because this will be the least acidic. The most acidic is methyl alcohol, so the fastest reaction will be with this. So this is the reactivity order. Now for this reaction, water should be continuously removed because to shift the equilibrium in forward direction. To shift the equilibrium in forward direction. That is Lee-Cattley's principle. So now coming to the mechanism of this reaction, mechanism part of this reaction. Before this, let me give you some examples. So we have looked at this. CH3 COOH reacts with methanol in presence of acid. So we have water molecule removed here. So this gives you CH3 COOCH3 plus water so we have this reacts with again look at this, water molecule is removed here, so the main product is CH3 CH2 COO C2H5. So we have these types of esters. So look at this reaction very carefully. We have looked at this RC double bond O, that is labelless isotopic oxygen. This reacts with HOR prime. Now during this reaction, as I told you, H plus ion is coming from alcohol, so these label oxygen will be removed and the the product will not contain any label oxygen. But if I do the reaction here, RC double bond OH reacts with H O level oxygen. So the alcoholic oxygen is labeled with isotopic oxygen. Then this reaction, the label oxygen will be present in the product ester. So this in fact labeling of this oxygen gives the mechanism that we are going to provide. In fact, this also proves the acidic character of these alcohols in this reaction. So coming to the mechanism part of this reaction, so we have these steps, starting with this RC double bond OH. If you look at this oxygen is having 2 lone pairs of electron. This reacts with H plus ion coming from the sulfuric acid, which is used as a catalyst. So this is a basic side, this is acid, so this reacts to give you RCO OH2 with a positive charge here. OH2 positive charge. with a positive charge here. Now this species is resonance stabilized, so we have electron here. So R C OH double bond OH positive. So the first step is protonation of the acid. This is coming from sulfuric acid. This is from sulfuric acid, not from alcohol. In the second step of this reaction, this protonated acid reacts with this alcohol. So we have this RC double bond O H OH. This reacts with alcohol. So now look at this. This oxygen being positively charged, this has got a very strong electron withdrawing character. When this withdraws electron density, carbon becomes electron deficient, that is electrophilic. On the other hand, we have this oxygen which is having two lone pairs, so this is acting as a nucleophile. So this nucleophilic oxygen acts as this electrophilic carbon. So we have electrophilic carbon reacting with nucleophilic oxygen when this gives rise to this compound. So RC OH OH, we have this OH bond, R prime, we have a positive charge on this oxygen. And in the third step of this reaction, look at this, RC OH 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 positive R prime. Now look at this oxygen being positively polarized, this is very strong electron withdrawing group, and this electron is withdrawn by oxygen. When this withdraws electron density, or this OH electron is transferred to this oxygen, we have H plus ion. This H plus ion is taken up by OH, and when this gives you RC OH OH2 positive here, then we have OR prime, and finally this oxygen containing two lone pairs of electron, an electron is transferred between carbon oxygen, and this withdraws and leaves the system with electron. When this gives you RC O R prime, and finally this releases the H plus ion which was furnished by, that is, this H plus ion is acting as a catalyst. So we have RC double bond O R prime. If you look at this, so actually in this reaction OH bond is breaking here, and this releases H plus ion. So this reaction proves the acidic nature of alcohol. So this is how we proceed. Or if you look at it, starting with this ester plus we have water, and the reaction is reversed to give you acid and alcohol. And some other reactions, look at this, like suppose we have this ester that will discuss in acids or acid derivatives. RC double bond O R prime also reacts with acid, and this gives you cross esterification. So RC O R double prime plus ROH, that is cross esterification, cross Fischer esterification reaction. Look at this, we have this RC double bond OX acid halide reacts with ROH. This is alcohol. So again we have this esterification reaction OR prime plus HX. So these reactions simply proves the acidic nature of alcohols. So for this reaction, the requirement is the acidic character of alcohol should be more, so that the reaction becomes faster, and this is in the forward direction. And we have discussed the acidic characters of alcohol, that is methyl alcohol is the most reactive and tertiary alcohol is the least reactive for this reaction. So look at this, we have this acid. This reacts with CH3OH in presence of catalyst. So the product will be COOCH3 CH3 COOH plus OH CH2, that is benzyl alcohol in presence of H plus ion. So we have this CH3 C double bond O CH2. So this is what we call as Fischer esterification reaction. So keep in mind, in Fischer esterification reaction, which proves acidic nature of alcohol, the OH bond of alcohol is to be break, and in the reaction acid will behave as if like a base and alcohol will behave as if like an acid. So these are the two important reactions which develops or proves the acidic nature of alcohols.